Hello friends, welcome to engineering tutorial. Now in my previous video, I discussed some of the basic concepts related to electrical circuits regarding measurement of electric potential or voltage between 2 points, the current direction or the sign convention associated with flow of currents, and the sign convention related to voltage drop across a resistor connected in a circuit. So basically our discussion revolved around resistors, voltage, current. So in this video we are also going to keep our discussion very simple and basic, and it will be regarding resistors. It will be a very basic concept related to connection of resistors or modes of connection of resistors in a circuit, the various ways in which the resistors are connected in a circuit. It's a very basic thing, a very basic topic, but it is very important. Okay, so generally there are two ways in which resistors are connected in a circuit. Two ways. First is series connection, second is parallel connection. Now most of us, we have studied regarding series and parallel connection in class 10, now high school level. But still I am discussing this topic so that we go about discussing the basic concepts related to circuit theory in a systematic way. No matter how basic and simple the topic is, we are going to cover it. Okay, so this video is related to series and parallel connection of resistors. So we are going to discuss about the series and parallel connection separately. Okay, so let us first discuss about the series connection of resistors. So first we are going to discuss about the series connection of resistors. Now look at this circuit diagram. This is one of the most basic circuits you will find to depict series connection of resistors. It consists of a voltage source V with three resistors R1, R2 and R3. Don't consider now L1, R1, all that. Now just focus that there are three resistors R1, R2, R3, which are connected across the voltage source V, DC voltage source V. Now, here I said that this is series connection of resistors. This is a circuit which represents series connection of resistors. Now the first question that might be popping up in your head is that how can you say that this is series connection of resistors? Now, whenever the resistors are connected in series or parallel, there is certain pattern associated with, a unique pattern which is associated with those connections. Now, let's say a resistor R has two ends. We are just considering that for easier analysis. A left end L and a right end R. Here also each of the resistors R1, R2 and R3 have been represented by two ends. Left end of resistor R1 L1, right end of resistor R1 R1. Similarly, L2 and R2 are the left and right ends of the resistors R2. L3 and R3 are the left and right ends of the resistor R3. Now whenever you will find one of the ends of the resistor is connected to the other end of another resistor or the next resistor, again one of the ends of the resistor is connected to another end of the next resistor, in this type of connection you can say, this end-to-end connection, you can say that the resistors are connected in series. You can see here the left end of the resistor R1 is connected to the positive terminal of the battery. The right end of R1 is connected to the left end of R2. Similarly, the right end of R2 is connected to the left end of R3. and the right end of R3 is connected to the negative terminal. So there is an end-to-end connection in each of the resistors. The right end of one resistor is connected to the left end of the next resistor. The right end of this resistor is connected to the left end of this resistor, the next resistor. So there is an end-to-end connection. So wherever you will find end-to-end connection of resistors or any other impedance, let's say capacitance or inductors, you can say that they are connected in series. Okay, so they are connected in series. Now you can say that the current flowing through each of these resistors R1, R2 and R3 will be the same. The current flowing through R1, R2 and R3 will be the same. Now here L1, R1, L2, R2, L3, R3, they represent the left and right ends of each of the resistors R1, R2 and R3. Don't confuse them with any other thing. It simply means the L represents the left end, the R represents the right end. Here the right end of R1 is connected to left end of R2, the right end of R2 is connected to the left end of R3 and so on. So there is an end-to-end connection pattern which is emerging here. So wherever there is an end-to-end connection pattern, you will find out in any circuit involving impedance, let's say resistance, capacitance or inductance, it applies to all. You can say that the impedances, here in this case it is resistance, they are connected in series. And the current flowing through a series connection of resistors is the same. Means current I, the same current I will flow through R1, the same current I will flow through R2 and the same current I will flow through R3. So now let us derive the equivalent resistance of this series combination of resistors. Okay, let's see. Now we are going to derive the expression for the equivalent resistance of a series circuit or a circuit involving resistors connected in series. So we are using the same circuit with R1, R2 and R3 being connected in series across a voltage source V, a DC voltage source V, where the current I is the circuit current, the series current, which is the same flowing through the resistors R1, R2 and R3. Because in series connection the current through each of the resistances is the same. Now here VR1, VR2 and VR3 are the voltage drops across the resistors R1, R2, R3. Now pay attention to the polarities that have been given, plus minus, plus minus, plus minus. I have already explained in my previous video related to voltage drop across resistors that the resistors, they always absorb power. Okay, they always absorb power. So whenever current flows through the resistors, it will always be from positive to negative terminal internally through the resistors. So that's why the polarities are given like this, plus minus, plus minus, plus minus. Okay, now if we apply KVL in this closed loop, okay, if we apply KVL in this closed loop, we will get V, which is the total voltage across which these three resistors are connected, the DC voltage source, equal to the sum of the three voltage drops across the three resistors. That is, V is equal to voltage drop across R1 plus voltage drop across R2 plus voltage drop across R3. Okay. Now, this total voltage can be expressed as total current I, which is this total circuit current, the series current, into the equivalent resistance of this series circuit. Okay, the equivalent resistance of these three resistors combined. Okay, R equivalent is the equivalent resistance of the circuit. So the total voltage can be expressed as this: V is equal to I into Req, I into equivalent resistance, equals to the voltage drop across resistor R1 is I into R1. The voltage drop across R2 is I into R2. The voltage drop across R3, the resistor R3, is I into R3. Why? Because the same circuit current flows through each of the three resistors R1, R2 and R3, and the voltage drop across a resistor is the product of this current flowing through the resistor and the resistance value. So each of the voltage drops VR1 is equal to IR1, VR2 is equal to IR2 and VR3 is equal to IR3. Now in this expression I can be taken as common. So I is taken common, I into R1 plus R2 plus R3. So in the LHS and the RHS I gets cancelled out. So the equivalent resistance is given by R1 plus R2 plus R3, that is the sum, the simple sum of the three resistors that are connected in series, R1 plus R2 plus R3. So the equivalent resistance for resistors connected in series, any number of resistors connected in series, is simply the sum of the individual resistances. Suppose there would have been n number of resistors connected in series, it would have been R equivalent is equal to R1 plus R2 plus R3 plus R4 plus R5 plus dot 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 plus Rn, nth resistor, the sum of nth resistors that are connected in the circuit. So this is the conclusion. The equivalent resistance of a series resistor circuit is equal to the sum of the individual resistors involved in it. Simply the sum of the individual resistors. Here there are three resistors R1, R2, R3 connected in series, so the equivalent resistance is R1 plus R2 plus R3. Next we are going to discuss about resistors connected in parallel or parallel combination of resistors. Now we are going to discuss about resistors connected in parallel combination. Okay, so here in this circuit you can see again there are three resistors R1, R2 and R3 which are connected across a DC voltage source V, and the total circuit current is I. Now you can see there is a clear cut difference between the series connection and the parallel connection. In series connection there was a end-to-end connection pattern. Okay, it means that the right end of a particular resistor was connected to the left end of another resistor or the next resistor. Again this right end of resistor R2 was connected to the left end of resistor R3. So there was an end-to-end connection, the right end to left end, right end to left end, right end to left end, that kind of a connection pattern was followed in series connection of resistors. But here you can see the left ends of the resistors are in one side, the right ends of the resistors are on another side. Okay, the left ends are towards the left side, the right ends are towards the right side. All the left ends of the resistors, the three resistors R1, R2, R3, the left ends of the resistors R1, R2 and R3 are connected at one point. The right ends of resistor R1, R2 and R3, the right ends, okay, the three right ends, the right hand points are connected together at one point, and these 2 points are connected to a voltage source V. So whenever you find this type of connection pattern where the left ends are connected at a particular point, all the left ends of the resistors are connected at one point, all the right ends of the resistors are connected at another point, and those 2 points are connected across a voltage source, you can say that the three resistors R1, R2 and R3 are in parallel connection. Here L1, L2 and L3 here, these L1, L2 and L3 are R1, R2 and R3, sorry this is R1, by mistake I have written R2, this is R1, R2 and R3, they are the left and right points, left and right end points of R1, resistors R1, R2 and R3. So all the left hand points are connected at a particular point, all the right hand points are connected at a common point, and those 2 points are connected to the 2 terminals, positive and negative, of the voltage source V. Okay, all the left hand points of the resistors are connected at a common point, all the right hand points of the resistors are connected at a common point, and those two common points are connected to the negative and positive terminals of the voltage source V. So whenever you find this type of pattern where resistors are connected in, you can say, one above the other, with the left points, the left hand points of the resistors at one common point and the right hand points at one common point, you can say that the resistors are connected in parallel. So next we are going to derive the expression for the equivalent resistance for parallel combination or parallel connection of resistors. Now another important thing to take care of is that the voltage across each of the resistors R1, R2 and R3 will be the same, and it will be equal to V. So the voltage across R1 will be V, the voltage across R2 will be V, and the voltage across R3 will be V. In series connection of resistors, the current flowing through each of the resistors was the same. Here the voltage across each of the resistors is same. In parallel connection, the voltage across the parallelly connected resistors are the same. In series connection, the current flowing through the series connected resistors is the same. In parallel connection, the voltage across the parallel connected resistors is the same. So this is one of the fundamental difference between series and parallel combination of resistors. Next we are going to derive the mathematical expression for the parallel connection of resistors. Next we are going to derive the expression for the equivalent resistance of this parallel combination or connection of resistors. The same number of resistors we have taken, R1, R2 and R3, which are connected in parallel across a DC voltage source V. Now I already said that one of the unique properties of parallel combination of resistors is that the voltage across each of the parallelly connected resistors R1, R2 and R3 will be the same. It means the voltage across R1 will be V volt, the voltage across R2 will be V, and the voltage across R3 will also be V. But the current flowing through each of the resistors will be different. In series connection, the current flowing through the series connected resistors was same, and the voltage drops across the resistors was different. But here it is the opposite. The voltage drop across the resistors is the same, but the current flowing through the resistors is different. There we applied Kirchhoff's voltage law. Here we will apply Kirchhoff's current law, KCL. So when we apply KCL at this node, we get the total circuit current I is equal to I1 plus I2 plus I3. I is equal to I1 plus I2 plus I3. Now I already said that the voltage drop across the resistors R1, R2 and R3 is the same, which is V volt. So we can write this total circuit current I as the total circuit voltage V by Req, where Req is the equivalent resistance of the parallel combination of resistors. This is the expression for the total current, V by Req, capital I. Now each of the individual resistors current flowing through R1, R2 and R3, that is I1, I2 and R3, can be written as V by R1, I1 is equal to V by R1, I2 is equal to V by R2 and I3 is equal to V by R3. Current I is equal to V by R. The voltage drop across R1, R2 and R3 is V volt, the same. That is the property of parallel combination. Now here V can be taken as common from this expression. V can be taken as common. So we have taken V common here. So when we take V common, we get V into 1 by R1 plus 1 by R2 plus 1 by R3. So in the LHS and RHS, V gets cancelled out. Capital V gets cancelled. So we are left with the terms 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So that is the expression for equivalent resistance for parallelly connected resistors. So if there would have been n number of resistors connected here, the expression would have been 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4 plus 1 by R5 plus dot 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 up to 1 by Rn, the nth number of resistor. So here we can say that the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistors. In series connection, the equivalent resistance was simply the sum of the individual resistors. Here, the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistors. So that is the expression for equivalent resistance for parallelly connected resistors. Okay, so here we have discussed about the basic concept, very simple and basic concept related to series and parallelly connected resistors. I discussed about how we can figure out by looking at a circuit whether the resistors connected in the circuit are in series or in parallel. When you see that there is an end-to-end connection pattern in resistors, means the right end of a resistor is connected to the left end of the next resistor, again the right end of the resistor is connected to the left end of another resistor, then we can say that the resistors are connected in series. And in series connection, the current flowing through the series connected resistors is the same. In parallel, all the ends of the resistors, the left ends of the resistors are connected at a common point, all the right ends of the resistors are connected at one common point, and those two common points are connected across a voltage source, the positive and negative terminals of a voltage source. This type of connection pattern is observed in parallelly connected resistors. Now this left and a resistor does not have left or right ends, it is same on either side here, but just for the sake of understanding I have used the term left and right side of a resistor, just to make you understand, to get acquainted with the pattern that emerges in series and parallel connected resistors, so that you can easily understand it. We have just named left and right end. In series connection there is simply end-to-end connection. One end is connected to the other end of the resistor, another end is connected to the other end of the resistor. In parallel connection, all the ends of resistor are connected at one common point and all the other ends are connected to one common point. Okay, so that's why I have used the terms left and right ends, so that you can say that all the left ends are connected at one common point, all the right ends are connected at one common point, and those two common points are connected across a voltage source. Similarly, in series connection, I have used the term left and right end, so that we can say the right end of resistor is connected to the left end of R2, the right end of R2 is connected to the left end of R3, and so on. So we can say that this resistor or the combination of resistors are in series. So here we have discussed about some of the basic concepts related to series and parallel connected resistors and their expression for equivalent resistance. Now in my next video we will solve some tricky circuits involving series and parallel connected resistors, so to get a better idea of how we can solve circuits where there are many number of resistors connected in different ways, and we have to figure out whether a particular set of resistors are in series or in parallel, and we calculate the equivalent resistors. So I hope you liked this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.